All right, today we're going to get into something pretty cool, the controlled release of stored electrical energy. We are talking all about the discharging of capacitors. You know, how they go from being fully juiced up to completely empty, and the really elegant physics that makes it all happen.
So think about it. A charged capacitor is kind of like a tiny, coiled spring of electrical energy. It can just sit there, holding that charge, sometimes for days. So the big question is, how do we get that energy out? How do we uncoil that spring exactly when we want and at the speed we want?
Okay, so here's our game plan. We're going to start with the absolute basics of what discharge is. Then we'll see what it looks like on a graph and introduce a super important idea called the time constant. After that, we'll roll up our sleeves and solve some problems, and then finish up by putting your new skills to the test.
Right. First things first. What is actually physically happening when a capacitor discharges? Well, it really all comes down to the behavior of electrons. Okay, picture this. We've got our charged capacitor. One plate has way too many electrons, making it negative, and the other plate is missing electrons, making it positive. As long as they're separated, nothing happens. But the moment we give those electrons a path, like connecting a resistor to complete the circuit, well, that's when the magic starts.
So here's the real driving force. All those electrons are crammed together on that negative plate, and they are all repelling each other. It's like a room packed with people who all want to get out. The second we open the door, by closing that circuit, that repulsive force just shoves the electrons out into the wire. But here's the crucial part. As electrons start to leave, the room gets less crowded, right? That repulsive force gets weaker, which means the rest of the electrons leave more slowly. And that's why the discharge isn't just one big poof. It actually slows down over time.
Now, this whole slowing down process creates a really specific, really predictable pattern when you graph it. Let's take a look at what that is.
And there it is. This graph shows exactly what we were just talking about. See how steep it is at the beginning? That's the charge dropping super fast when that repulsive force is at its strongest. But then, as the charge runs out, the curve starts to flatten. The discharge rate is slowing way down. This classic shape has a name. It's called an exponential decay curve.
So, what is exponential decay officially? It's any process where the rate of decrease depends entirely on how much stuff you have left. The more charge you have, the faster it leaves. The less charge you have, the slower it leaves. And here's a fun fact. Theoretically, it never actually hits zero. It just gets infinitely closer. In the real world, of course, we consider it discharged after a certain point.
And what's really cool is how consistent this is. It's not just the charge. The voltage and the current follow the exact same pattern. They all decay exponentially, and they all follow this same core equation. You take your starting value, that's what the little zero subscript means, and you multiply it by E raised to the power of negative T over RC. It's the universal formula for discharge.
So, we know the discharge slows down, but that begs the question, just how fast or slow is it? To answer that, we need to talk about one of the most important ideas in all of circuit theory, the time constant.
I mean, it's a fair question, right? We need some kind of standard measurement for the speed of this decay. We can't just say a circuit is fast or slow. We need a number, a value we can actually use. And that value, my friends, is the time constant.
The time constant, which we represent with the Greek letter tau, has a very specific definition. It's the amount of time it takes for the capacitor's charge or voltage to drop down to about 37% of whatever it started with. Now, I know what you're thinking. 37%? That sounds super random. But trust me, it's not. It comes directly from the math, and we'll prove it in a second. The best part is how easy it is to calculate. You just multiply the resistance by the capacitance. That's it. Tau equals RC.
So where on earth did that 37% come from? Let's check the math. We start with our trusty voltage decay equation. Now let's ask a question. What happens at the exact moment in time when T is equal to our time constant, RC? Well, let's plug RC in for T. The RC on the top and the RC on the bottom cancel out, leaving us with e to the power of -1. And if you punch e to the -1 or 1 over e into your calculator, what do you get? Yep, approximately 0.37. So after one time constant has passed, the voltage is always 37% of its original value. It's not random at all. It's built right into the physics.
Okay, the theory is solid, but the real test is seeing if we can actually use it. So let's shift gears and put these equations to work with some real-world problems.
All right, here's our first one. We've got our capacitor and resistor values, and the goal is to find out how long it takes for the voltage to drop by half. Now, notice this is different from the time constant, which is how long it takes to drop to 37%. So this will take a little more work.
Okay, let's walk through this. Our target is t, the time, and it's stuck up in that exponent. So step 1 is to set up our decay formula, where the voltage ratio, V over V naught, is 0.5. Step 2, we plug in our numbers for R and C, and you gotta love how the microfarads and megaohms prefixes cancel each other out nicely. Now step 3 is the key move. To get t out of that exponent, we have to use its inverse function, the natural logarithm. Once we take the natural log of both sides, t is free, and it's just a bit of simple algebra to get our final answer, 0.87 seconds. Not too bad.
Okay, let's dial up the complexity. This next problem has 5 parts, and it's going to make us use just about everything we've learned so far. This is a great one for tying all the concepts together.
Let's break it down. Part A is just our basic Q equals C times V. Part B is good old Ohm's law, V equals IR, to find the initial current. For C, we use our new formula, tau equals RC, and find the time constant is 50 seconds. Now part D is where you can be clever. 100 seconds is exactly 2 time constants. This means the charge is dropped to 37% of its value, and then 37% of that new value. So we just divide the initial charge by E squared. For the last part, we go back to the full decay equation, plug in our target charge, and solve for t using natural logs, just like we did in the last problem. See? It all connects.
Okay, your turn. Take a look at this one. Maybe even pause and try to work it out yourself. We're looking for the initial charge, the charge after 2.8 seconds, and the voltage at that exact moment.
So how'd you do? Let's check it. First, the initial charge is just C times V, which gives us 240 microcoulombs. For part B, you first need the time constant, which is RC, and then you plug that into the big decay formula to find the charge after 2.8 seconds. And finally, for part C, once you have that new charge, you can just use the basic V equals Q over C formula to find the new voltage. Simple as that.
To finish things off, let's do a quick lightning round. A few exam-style questions to make sure these ideas are really locked in.
Okay, let's fly through these. For question 1, you find tau with RC, and then you use the natural log method to find the specific time. Question 2 is a little tricky. The initial current doesn't need any decay formula. It's just Ohm's law, V over R. And question 3 is a great one. It's the same decay equation, but you have to rearrange it to solve for the time constant itself. It's a great test of your algebra skills.
You know, if you only remember one thing from all of this, let it be this. The time constant, tau, is the boss. It controls the speed. A big time constant means a slow, gentle discharge. A small time constant means a really fast, sudden burst of energy. That's the whole story in a nutshell.
And that really brings us to the big picture. This isn't just about equations, it's about engineering and design. Controlling how quickly energy is released is absolutely fundamental to so much of our technology. Think about a camera flash, a defibrillator, even the timing circuits in every computer. So I'll leave you with this question to think about. Where else is this precise control over timing not just helpful, but absolutely critical?